Okay, so welcome to the plane curves class today. So today is a topology day, so to say. So it means we want to use Bézout's theorem essentially to answer topological questions on curves. So the question today is, or the goal is a topological description of real or complex smooth projective curves. So smooth projective curves. Over R or C. So these are really two completely different cases. So the topology, of course, over the real or the complex number is completely different. I mean, this is a one-dimensional real picture. This is a one-dimensional complex, hence two-dimensional real picture. But both of them can use Bézout's theorem in a nice way to show what that looks like. So in particular, that also means, as I say, it's sort of a topological day that I'll use something from topology, which you may or may not know, but I mean, as usual with topology, all these statements are somehow intuitively clear that they should be true. If you want to actually prove them, it's more work. But in that sense, most of the proofs or constructions or definitions that we give today is more like sketch proofs and sketch definitions. But it should be always, I guess, clear geometrically what's going on. So that's also then like this today's class sort of like an example that algebraic geometry has many relations, not just to algebra, but also to other fields like topology, which should be sort of clear, because the goal of algebraic geometry is to say what objects look like just from given their algebraic description, and what they look like often just means topology. So let's start with the first case, namely the real number. So curves over the reals, and we started a little bit with that last week already. So the situation will be, so always f is a smooth projective curve now over R. In this first case, and we want to consider its zero locus. So often today I will just say the curve looks like, of course I mean then the zero locus of the curve looks like, the set of points looks like. And this set of points, so which we call V of f, then sits in the projective 2 space over R, so on the real projective plane. And we had seen already that it is then a one-dimensional compact manifold, which means that it locally looks just like a real line and compact. It's just a topological statement. We had also seen that this means a one-dimensional compact manifold is always a union of loops. So a curve might look like this. And if we are drawing the affine picture, it might also be that there's a component that is infinite. So that means it goes to some point at infinity and then comes back down from the other side at infinity. But topologically, that's also a loop. So oftentimes we would just draw affine pictures, and then, because you should consider that a loop as well. And the question, of course, would then be, if you're given the degree of the curve, what can the number of loops be? And we had seen in the example last time that for degree 1 and 2, you always have one loop. So for degree 1, that's sort of clear because you just have a line going together at infinity, which is one loop. And for degree 2, we had also seen that it's the case. So the question is, given B, which is the degree of f, what can the number of loops be? And we had seen already that for d equals 1 and d equals 2, we always have exactly one loop. So for higher degrees, in fact, in the real case, it's not really determined what the number of loops is. We just have an upper bound, and that will be the result, essentially. But before we start with that, let me just give you an idea how you can actually construct such curves that might look like this. So for higher degree, well, a way to construct examples is actually quite geometrically quite intuitive, is to start with a singular curve and then deform the equation a little bit by a constant. So a way to construct example is to start a singular curve, which is not allowed at the end, but we could start with that and then deform it. So which I mean the following. So let's do that. I have one example in degree 3 and one in degree 4. So let's start maybe with the singular curve, somehow the standard singular curve that we've seen so often already, which is y squared minus x cubed, which where the affine picture looks like this. And if you want to think of it as a projective curve, then you just make it a z here, so you marginalize that, and then there's a point at infinity here, and also here, which is the same. So that will not be a curve that we want to consider because it's singular, but we call this f. Write down the affine equation like that. Then what we can do is, first of all, so the locus that I've drawn here, of course, is the locus of points where f is equal to 0. And in the other regions of the plane, so that means here and there, of course, f is not equal to 0, which over the reals means it's positive or negative. And it's quite easy to see what's the case where. So here's the origin first in the curve. So that means if we're going up here, so in that region where y is positive or y is negative, but x is 0, that will be a positive number here because of the y squared term. So that means here, let me just draw a plus here, which means in that region of the plane, f is actually greater than 0. And if we're in that region here, then x becomes large and y is 0. So that means because of the minus x cubed that here f will be negative. And of course, inside here f will be negative as well. So essentially at each point when crossing the curve, you change from plus to minus. And on the curve itself, you have f equal to 0. So that is a singular curve. And the idea is now to deform that curve by just adding a small constant. So by either consider like an f minus epsilon or an f plus epsilon, where epsilon is a small positive number. So what happens then is, of course, like from the topological intuitive picture, if we just add a small number, the picture shouldn't change too much. So it still looks sort of like this, but the curve will become smooth. And so the only question is what happens around the 0 point. And of course, if we have an f minus epsilon, that means then you plug in the 0 point, then this new function f minus epsilon will become negative. Yeah, because this is 0 at the origin, so this will be negative. So that means the origin will now be in the negative part of that. Right? So the negative part is that. And the origin will be in there, so the curve still looks very similar to that as it looked before. So outside of the origin, you probably can't tell the difference just from looking at this qualitatively, but the 0 point will now be in the negative region, so that means the curve will look like this. Okay. This is the negative region, and this is the positive region. And so that means we have a curve now with one loop. Whereas if we do a f plus epsilon, then the origin will be in the positive region, which means that if the origin is now here, the curve will look like this. And so again, with a minus here and a minus here, and here's the plus. So that means at the origin now we have a minus, at the origin we now have a plus. So that's what's happening, and I guess that's from the intuition should be sort of clear that the curve really doesn't change very much. The singular point will become smooth, the local part, and whether it looks like this or that. That means whether this crossing is resolved like this way or the other way depends on whether you take plus epsilon or minus epsilon. And so you see that you get two curves with a different number of loops. So here we have obviously one loop, and here we have two loops, which means already that we see that there's the degree doesn't determine uniquely the number of loops. So we have choices here. We can actually do a very similar thing, and just another example of degree 4 curves. Very similar strategy. We start with f, a singular curve. And for example, we could take, just starting from the geometric picture, a union of two ellipses. This. They centered around the origin, for example, so say 0 point. And, well, I mean, the equation would be just the product of two ellipses, and that might be sort of like, whatever, 2x squared plus y squared minus 1, that's an ellipse, and then you take an ellipse with a radius in the other direction to x squared plus 2y squared minus 1. Well, actually, it doesn't matter too much, so you just take a product of two equations which are both an ellipse, and then it looks like this. Same strategy as before. What happens outside? Well, outside all of these terms grow will be positive, so that means we have a plus outside here. And then at every order, when you cross the curve, you switch from plus to minus and vice versa. So here there will be a minus, and in the middle we'll have a plus. In the middle you can just see if you plug in the origin, you have minus 1 times minus 1. And you do the same as before. Now you just change f to an f minus epsilon, f plus epsilon. And that again means that the curve will not really change very much, but the singular points will go away. And in such a way that for f minus epsilon, the points where before we had a 0 value will now have a negative value. So that means these 4 points will move into the negative region, which are those 4 ones. Oh, and that means the curve will look like this. So a smooth curve like this, and the positive region is still here. Here's the negative region, here's the positive region. And the same way as before, the curves will be resolved the other way. If you do an f plus epsilon, then this will become in the positive region. It will go move into the positive region. And then it looks like. And again, so here you have a minus, and here there's a plus, and here there's a plus outside. So that means, again, we have different number of loops. So here we have 2 loops, here we have 4 loops, so the number's already sort of quite big. So here we have 2 loops. In that case, they are both bounded, and also here we have 4 bounded loops. And so the question is, what is the bound? So can we get more than 4, and depending on the degree, how many can we get? Okay. Right. Now we need one thing from topology, which is related to the topology actually of the real projective plane, which we had studied like 2 or 3 weeks ago. And for that, we just have to recall that the projective plane could be modeled by taking like an upper half sphere, which is sort of like a disk, and then identify opposite points. Mark, before we can actually prove the theorem about the loops. So there's a remark about which I want to call even and odd loops. So let's recall that the ambient space where everything lives in, so P2 over R, is a disk, or rather an upper half sphere, but which is the same topologically, with opposite points identified on the boundary. which means if I try to draw a picture with the infinite points, then P2R looks like that, where like this point and that point, I mean, they are identified here, that's the same, but also this point and that point is identified and so on, which is hard to draw. I mean, it cannot be embedded in R3, let alone in R2, not on the board, but I mean, that's the way. So the best way at the moment is just imagine a disk and we identify opposite points. That would be a picture of the real projective plane. And if we have a loop inside there, there's essentially two ways what they can look like. So we have two kinds of loops, which is due to the topology of the real projective plane. And you could have either a loop that separates the projective plane into two parts, or we have loops that don't do that. So for example, if we take an obvious loop like this here, would be a loop such that the complement has two components, right? So we have an interior here, and we have an exterior out here. So there's an interior of the loop, and here there's an exterior. The interior and exterior can really be distinguished because the interior here is obviously just a disk, again, topologically, an open disk. But the exterior here, as there's still this identification of the opposite points, is actually a Möbius strip, topologically. Right? So the interior here is a disk, and the exterior is a Möbius strip. And so that means it looks sort of like this, right? It's an unoriented surface, so something like that. Which you could see sort of, I don't know if you can see that topologically that this is true. We just had it in my topology class, but you're probably not in there. So if you, for example, take a so the characteristic of the Möbius strip is that it doesn't have an orientation, right? So you can move around the thing and end up with the opposite orientation. So there's no two sides, but it's a one-sided surface, so to say. And if we have like a small orientation here, like this, going that way, then of course I can move around that thing. But if I move across the border here, like there, and come up here, then this orientation will actually swap sign and go into the other direction. And that means that you don't have a natural orientation on that thing in the same way as you have it on the Möbius strip. So that's one type that you could have. In any case, the most important thing is that it really divides the thing into two parts, which seems natural, but there are also loops that don't do that. Namely, as we identify opposite points, something like that would also be a loop in that space. Because that's the same point as that. So obviously a loop. It looks like, for example, a thing here. And that one does not divide the plane into two regions, right? Because I can cross this and that's the same as that. So that means here the complement of the loop is just one, has just one component. It's really like a completely different topological picture. So here there is no interior or exterior, just the complement of the loop is a disk, and there's no two components, right? So here it divides the plane into a disk and a Möbius strip, and here it's just a disk. So these are the two possibilities that might occur, and that's not really a question about the loop being bounded or not. So if I want to have something like that here, then I need to cross the boundary, but I could also have a curve. Let me just draw a small picture here. For example, like this. And so that's also a loop, and it divides the thing into two regions, although it's unbounded. And these two types, I want to call those ones here even and odd. These I call this even loops. And this is an odd loop. I guess you can sort of topologically imagine that this is true. So if you know some topology and had seen the fundamental group, then the region for that topologically is just that the fundamental group of the projective plane is Z mod 2Z. So it has exactly two elements, 0 and 1, and that corresponds to the two elements. Let's see. Just in case you had seen that before, then that would be the, of that statement, that would be the correct way of saying that, right? A loop is an element in the fundamental group, and that has two elements, so it can be either the one or the other type. So the one thing that we'll need from that, and that really plays a role in the proof afterwards, is that at the end of the day, we only care about the number of loops, right? So that was our goal. The question determined the number of loops that we can have in such a picture here. But in fact, we can see from that description already that there can actually always be at most one odd loop of such a curve, and all the others would have to be even. That is just because if we have one odd loop only, then the complement of that thing is already a disk. And in a disk, every curve has an exterior and an interior. So that means there's no room in the real projective plane for two non-intersecting. We have a smooth curve, right? So they cannot intersect, for two non-intersecting odd loops. So let me just write something down here. So, but maybe just in brackets in case you know. So topologically, even and odd loops correspond to the two elements of the fundamental group of pi1, that's the usual notation for that, of P2 over R, which is Z mod 2Z. And so the zero elements, or the even ones here, are the contractible ones. So that's, I mean, in the language of fundamental groups, I would say this is a contractible loop in the space. You just move it to a point. This cannot be contracted. And as I said, so the most important point that we'll need now is note that in a smooth curve, we can have at most one odd loop, namely its complement is then a disk, and in a disk, every loop has an interior and exterior, so must be of the even type. And this is even. And so whenever we have many loops, even here, I mean, here we can obviously see this. I mean, these loops would all be even, they're all contractible. In that picture here, actually one would be even and that would be an odd loop, right? So that's pretty much the picture up there. Okay. So with that, we can then show our statement proposition, which also has a name, and it's called Harnack's theorem. And that says that every smooth projective curve over R, so the things that we look at here, has at most a certain number of loops. And the number here is very close to the number that we had last time for the bound on singular points, namely D minus 1 choose 2, but a plus 1. So that's the statement. So if we look at the numbers, by the way, here what they are, so it's just, it's one more than the number for singular points that we had last time. So for 1, 2, 3, 4. So this number here, E minus 1 choose 2 plus 1. will be, so here it's 1, here it's 1, we've seen that already. So here we get a choose 2, which is 1 plus 1, which is a 2. And there we get a 4, choose 2, which is 3, plus 1, which is 4. And so that means our example that we had seen here are, in fact, they do reach the maximum number. Right? So for cubics, we can have at most 2 components, which we had seen in that example, that kind of curve. And for degree 4 curves, we can have at most 4 components, where we had seen an example here. In fact, one can show that this bound is really sharp. That means for every degree, you can find a curve, a smooth curve that does have this number of loops with similar techniques than that. So you start with a suitable singular curve and then deform it a little bit. So as promised, that's an application of Bézout's theorem. And what is surprising, I guess, is that it's not just it doesn't just follow from Bézout's theorem, but also the proof of that is pretty much the same as the proof last time, where we showed that a degree D curve has at most D minus 1 choose 2 singular points when it's irreducible. So we will just see why. So let me just write down this proof here, and then you'll probably recognize that many things happen the same as before. So again, of course, we do that by contradiction. So we assume we have at least one more. We assume there are at least D minus 1 choose 2 plus 2 loops. And by our remark up there, this means that we can have at most one odd loop, and that means at least 2 D minus 1 choose 2 plus 1 loops have to be even. Our remark. So by the remark, at least D minus 1 choose 2 plus 1 of them are even. And so that means the picture will look like that. So we have a certain number of even loops when we draw them in the finite part. So they just have an interior and an exterior. And then we will have one more, which might be even or odd. Let me just draw it odd, but it really doesn't matter. So that might be a picture of the curve. Okay. Draw that with colors, then that would mean so the even ones are those ones here. And then there's one more component. And now we do the same, sort of the same thing as last time. We pick a point on each of the even loops, on these even loops here. So pick a point pi on each of these loops. So that means here we'd have, for example, a P1, a P2, here a P3. And then that means there's D minus 1 choose 2 plus 1 points. And on one other loop, like on the last one, we choose D minus 3 more points. And 3 more points. Well, then Qi on another component. There must be one other, at least because we have this number here. But they can be all the same. So it might have the Q1, Q2, whatever it is. And so again, I write D minus 3 here. So we have already solved the problem for D equals 1 and 2, right? So we can assume D is at least 3. So in the proof here. Well, that's the picture. And what we do now is the numbers here are actually exactly the same as before. We see how many points we have. So we have a total number of D minus 1 choose 2 plus 1 and then plus D minus 3 points, which is exactly the number of points that we had in the proof for the number of singular points last time. And there we had computed what this is. So this was actually a D choose 2 minus 1. And then we had a lemma last time saying that there is a curve of degree d minus 2 through all these points. So by the lemma from last time, we see that there is a curve g maybe through all these points. So as I said, if you recall from last time, then what we did there was we had a number of singular points, which were the pi'd. And then we said we pick all these singular points and then some more points on the curve. And there was then a curve g through all these points. And also of degree d minus 2. So that's exactly the same as before. So let me draw a picture here. So it passes through here P3, P2, P1, and then all the q's. So it might look something like that. That would be G, and that is F. And in our case of the singular points, we could then say, well, the point of the proof was that the intersection points of F with G for the singular points of F were count at least with an intersection multiplicity of 2, because we had a singular point on F. So they had at least 2 of them, and the others we didn't know. If you look at that picture, they are not singular points, but as these even loops divide the plane into an interior and an exterior, this means that the curve G, when it enters the interior, it also has to exit the interior again. So that means for each of the even loops, we will get not a point with intersection multiplicity 2 in general, but we will get 2 intersection points, which we haven't accounted for yet because we took all the PI on different loops. Right? So that means there will be here like a point P1 tilde, and here P2 tilde, and here P3 tilde. So it's a different point, but again, the effect is that we can count those PI twice, and we get more points. It might, of course, be that, well, the curve just touches, so in case G just touches here, then it doesn't move in and out, but then we have a multiplicity 2 as well. Right? So that would be a more special case, but in general, it will look like this. Well, and that leads to that we can do exactly the same argument as last time. So we count the total number of intersection points that we have seen, and which is this number times 2 plus d minus 3, and that's bigger than the Bezout number by the exact same calculation as last time, that the numbers are exactly the same. That was bigger than d times d minus 2. And that means that G must be a component of the curve. And then, as we've assumed, I didn't write it down, but we should definitely have irreducible. Forgot this, we'd also had this last time. That means that we have a contradiction, right? Because that is an irreducible curve and G has smaller degree, it's d minus 2, so F cannot be a factor of that. So say each point Pi leads to a second point of intersection, which is called Pi tilde in the picture, and that is as these loops are even. Means you enter the interior and then you leave the interior again. So that means we have a total number of intersection points is at least, and then you take twice the number of points Pi, namely d minus 1 choose 2 plus 1 and then plus d minus 3. So that's exactly a computation that we did last time. The result was d minus 2 plus 1, which is greater than d minus 2, so greater than the product of the degrees. And so that means by Bezout that F and G have a common factor. Which is a contradiction to F being irreducible and having bigger degree than G. So that is the contradiction here, and that proves the theorem by contradiction. So as I said, the numbers and the general idea, find some points that count twice and then add some more points, and you just add up the intersection multiplicity. Is really the same as before, but here you prove like a completely different theorem. So it's like over the real numbers, the topology. The other was over an arbitrary field, the number of singular points. And it sounds like totally different questions. But from the point of view of the proof, they are really not very much the same. Yeah, and so that tells you essentially what the topology of a real curve can be. So it's a number of loops, and you have a bound which is given by Harnack's theorem, which is also then sharp, as you can show. It doesn't tell you yet how these loops lie relative to each other, which is also like an interesting question. I don't want to address this here, but if you have a couple of loops, so several loops, then they might be, I mean, in the case where you have even loops, most of them are even, you could ask whether they lie inside each other or not. So to say, an even loop divides the plane into an interior and an exterior, and you can really say which is which, because one is a disk and the other is a Möbius strip. So that would be really the interior, and this one outside is not. So if we have, so here I've drawn the loops in such a way that each loop is on the outside of each other loop. But we had a picture for degree 4, I think, where this was not the case, right? So 1 degree 4 picture was like this, right? Where one was in the interior of the other. That we had 2 loops and one is in the interior of the other. So that there could be more things that one might look at, but we don't want to do that here. Okay. Yeah, so that's about the real curves. There any questions there? Right, it's a nice topological result, I guess. Yes, so then if not, let's move on to the complex case. And that is, of course, a little more complicated because we now are talking about real 2-dimensional pictures. And of course, the first would now live in P2 over C, which cannot really be drawn as that's 4-dimensional space. But we are only interested in the topology without its embedding, so in the same way as we did it here. So we don't care how the loops lie inside or outside of each other, but just how many of them there are. And we consider the corresponding questions now for complex curves. So that's the second case. Maybe curves over C. And they also start with a remark as we did for the real ones. So in that case, so let's say again that F be smooth, projective, curve over C. So in the case of the complex numbers of an algebraically closed field, we already know even that smooth implies irreducible. Particularly, it will also be irreducible. Right? Because if we had 2 components, they would meet by Bezout. And again, we want to describe its set of points. So V of F now in E2C, where, as I said, I don't really care that much about the embedding, but just of the topology of the curve itself. So in that case, of course, so now in the complex case, V of F is a complex 1-dimensional, so it's still a compact space, of course. It's a zero locus of an equation in a compact space. So it is a compact, but now 2-dimensional, or say 1-dimensional complex manifold, and that's real 2-dimensional. So i.e. a 2-dimensional real manifold, which one would probably just call the surface, right? So something 2-dimensional. There's a bit confusion going on as for algebra in the sense of algebraic geometry. It's still a curve, but topologically it looks like a surface. So again, we have to talk a little bit about the topology of such compact two-dimensional surfaces in P2. In the same way as before, in the real case, we said, well, though, it will be a union of loops. So that's not so easy anymore in the two-dimensional case. I mean, there's two-dimensional smooth connected manifolds that are not just a sphere, like, for example, a donut or something. And so there's really something happening here. And there's like 2-3 things from topology, again, that we have to borrow, but hopefully, I mean, we can give you the arguments why it should be true. So let me just put it as a note. Or maybe I should better say something like one can show, so that's all. The first thing is that such a surface that comes from a smooth projective curve over C is actually an orientable surface. So that means you cannot have something like a Möbius strip that has only one side. So let's V of F is an orientable surface. What has two sides. And the reason for that is just very vaguely here, of course, because we're doing topology, which is not really the scope of this class, is that the curve itself, so like the tangent spaces of the curve, we talked about this, so at each point, is it's not just a real plane, it's not a real two-dimensional vector space, but it's actually a one-dimensional complex vector space. And a one-dimensional complex vector space has more structure than a two-dimensional real vector space because it has a natural multiplication with I, like the square root of -1, which gives a 90-degree rotation of that plane. And that's naturally defined at each point of this curve. And so that means every point has a natural, like, clockwise or mathematically positive counterclockwise rotation on it, which just means that there is a natural orientation. Right? Orientation means you know what's turning right and what's turning left. And there's just a well-defined way of defining that at every point. So that's the very short words, the reason for that. So the tangent spaces, so TPF, are one-dimensional complex vector spaces which then of course have a natural multiplication or scalar multiplication by the imaginary unit by I, which gives a positive, so gives everywhere a well-defined positive rotation by 90 degrees. Well, that means at each point I can say what's turning right and what's turning left. So that's well defined over the whole surface. And that's exactly that is an orientation. So right? If I wanted to define what actually is an orientation, so then it would be something like that. It's a continuous way to assigning at each point a way of saying what rotation to the left and to the right. And that naturally exists by that complex structure on that. So that means we always will get an orientable surface. And the second thing that one can show is that one will actually always get a connected surface. So that's very different to the real case where we really had disjoint loops. But here I claim that V of F is actually connected. So that means we have an orientable connected surface in P24. And the reason for that is also said very quickly is that it's very similar to the argument here that we had that a smooth projective curve is irreducible, where we said, well, if we had two components, then we have Bézout's theorem, and Bézout's theorem tells us they would meet and there would be a singular point. The point is that one can show there is a Bézout type theorem in algebraic topology, just without using algebraic geometry, but in algebraic topology as well, meaning that a two-dimensional complex manifold inside P2C also has a notion of degree. And when you intersect two of them, you will get a number of intersection points, which is the product of these degrees. And then you have the same argument as before. If you had two of them, they would have to intersect. And where they intersect, there would be a smooth point, and we don't have a smooth point, and that's why it must be connected. So it's the very same argument, a very similar argument to that up there, why a smooth projective curve is irreducible. You can use that also to show that it's actually connected as a topological space. But of course, for that, we need this Bézout type theorem in topology, which is like the scope of an algebraic topology class. So we'll clearly not do that here, just mention that. So say there is a Bézout type theorem also for, what is it, compact two-dimensional manifolds in P2C. Namely in the following way. So each compact two-dimensional manifold in P2C has a notion of degree. Of course, it's not so clear even how to define that, because it's not given by a polynomial. I mean, so you cannot just say it's the degree of the polynomial. It's just a subspace in P2C. But the rough idea is similar to that fundamental group things. I mean, so in algebraic topology, there's ways to attach groups to topological spaces, just in the same way as the fundamental group. And the fundamental group measures one-dimensional objects in that space. And there's also groups that measure two-dimensional objects in that space, namely this here. And in such a group, that would be called like a homology group of that space, such a manifold will be of a class. And the group happens to be the integers here, so the class is just a number, and that can be used to define the degree there. But I really don't want to go into details here, but just say there's a theorem like that also for two-dimensional manifolds that in particular implies that any two of them will intersect. And so that means if we had a disconnected thing, then each of them would be a two-dimensional complex manifold, and they would intersect, and there would be a singular point. So any two of them will intersect, leading to a singular point, which we have included, which we have excluded. So that is there, the complex picture is really very different from the real one. So we do get a connected space this time. It's a two-dimensional manifold, compact, and it's orientable. And then there's one last thing, or maybe not the last thing, but one thing that I want to put here into that remark. What could that look like? So you have a surface that's a manifold, so it means no corners or anything, no singular points. Looks locally like an R2. It's orientable, so it cannot be anything like a Möbius strip or some compact version of that. And it's also connected, so it has only one component. There's actually in topology a classification for that. Namely, any, I do not forget anything, any connected and orientable compact two-dimensional manifold. So what we have here, the manifold must essentially look like that. So it starts, you can start with a sphere and then have a couple of handles here, which means like we might call them holes. which is sort of a donut with a certain number of holes, not just with one hole, but with a certain number of holes. That's the only thing that can look like. So that's again a theorem from topology, but it's sort of also intuitive in the sense if you try to imagine a picture in your head of a surface that doesn't have boundary, it looks smooth everywhere, it cannot twist itself because it's orientable, and then it should be connected, then it can only be something like this. So it's say homomorphic to a sphere with a certain number G. It's usually called handles, if you want so, or holes, whatever you prefer. So, for example, for G equals 0, we have an actual sphere. And for G equals 1, we get the standard donut. And for G equals 2, we have a donut with an additional hole punched in and so on. So that's, again, a statement from topology. It's for maybe intuitive to a certain extent, but it clearly needs, a longer proof. But that's just to make sure what the question actually is. So that means if we start with a smooth projective curve over C like that, then this means that the topological type will be one of those. And we are just asking, of course, what we are interested in, what is this number of holes? And so what's this number G? This number G is usually called the genus of the curve. And there's many ways to define that. In fact, we will actually see in the later course of this lecture, so like in the last weeks, also completely algebraic versions to assign a genus to a curve. And which will then be the same number, but there's completely different approaches to that number. So that's a topological approach that works in the complex case and in no other case. So let me just call this the topological genus of that thing. So we call the topological, and we put this in brackets because all other definitions will be equivalent, but they can be like vastly different in the definition. Like that's a topological definition. As I said, we will have a completely algebraic one later on. Topical genus of V of F. So of the two-dimensional manifold. So our question will be, I can just say, or just as a remark, we will see algebraic ways to define this number. Number later on. So, and the question now, of course, is, so what is this genus? Of V of F, of course, and somehow again depending on the degree. So that's just to make sure what the question actually is, right? So in the real case, the one interesting question was, we had a disconnected situation. How many components do we have? And then it was clear that every component has just a loop, because the only one-dimensional. So the equivalent statement for that, any connected, orientable, compact, one-dimensional real manifold is just a loop. So there's not much to be done. But then the question was how many of them. Here it's not a question how many, because it's always connected, but we can have a certain number of loops, and we ask how many loops do we have. It's really the only topological invariant, in fact, of the thing. The only topological number that we can assign to that. Yeah, so that's about the question. Questions? You know what we want, right? So we want to compute that number. Oddly enough, it will actually turn out that the resulting number that we get is again the same number as in all the propositions that we had before. Right, oops. Right. So let's take another go. Compute G-plane. Right. So to do that, I mean, it's obviously a topological computation. We need a construction, so a tool to do this. First of all, a topological tool is the following construction. So it means the following 2-3 things, so like 50 minutes will be really like, again, entirely topological and not related to curves. And that means we start actually, then we call this X, such a thing up there, so a connected orientable compact 2-dimensional real manifold. Really long. Okay. A 2-dimensional compact. Connected wouldn't matter too much, and orientable neither, but let me just write it down. Orientable, connected manifold. So what we can consider for such a thing is what's usually called cell decomposition. So we say a cell decomposition of X is a partition of that space. So we write the space as a disjoint union of others and of a certain type of things, namely of points, of open intervals or open lines and open disks. So it is a partition of X into a certain number. Let me give this number already names. So say sigma 0 of points. So sigma 1 of open lines, so open intervals, and sigma 2 of open disks. Well, with some properties, it should be nice, sort of. In particular, it should be finite. And let me not define that rigorously, but just drawing a few pictures. So essentially, everything that looks reasonable there would be allowed. As usual, if you do topological things in a more rigorous way, it will get much more complicated, but let's not do that and ignore all these rigorous parts instead of drawing a picture. So for example, if we take a sphere, what I mean by that, so for X equals a sphere, would have the following thing. So a sphere, what you could do is, let me take a couple of colors. So I could take here a point, a 1 point, and then I take this blue thing here, like the equator of the sphere. That would be an open interval as a space. And then this up here, like the upper half sphere is a disk topologically, and the lower half sphere is a disk topologically. So if I take like in that case, the sigma 0 would be 1. We have 1 point, we have 1 open line, and we have 2 disks. So draw that maybe in these colors. So sigma 0 will be 1. There's 1 point. There's 1 open line. And there's 2 disks. So just having a trivial case doesn't work. I mean, the sphere itself is not a disk, so we somehow have to subdivide it in with a couple of points and lines. But of course, there's many ways of doing that, right? I mean, that's far from being unique. We could just start, for example, by doing the same thing just in the other direction, or which would still lead to the same numbers, but to different choice of these. So if I still take this point and now take for line this one, so not the equator, but this line here, and then we have the left half and the right half of the sphere, I would again have the same numbers, but of course it's a different cell decomposition, right? So the same numbers here again, So it's again 1, 1, and 2. But I, of course, can also take more. So I could take something like taking both together, sort of, which is something which will occur in a minute. So let me say I take 2 points here, this and the opposite one, and then I take this one. Maybe I should put this in that, and then do the same thing here. This. What I'm trying to draw in this picture is essentially those two together, like the blue lines. And then I get 4/4 of that thing, so like the upper left and upper right and lower left and the lower right. So there would also be a cell decomposition. Now we have 2 points here, so there's 2 points, and now there's 4 open lines, namely this one, the right one, the left one, the upper one, and the lower one. So there's 4 of them here, and now there's also 4 disks, right? So these orange ones, so there's 4. And of course, in general, you could imagine a picture with really huge numbers like that, right? You could just draw a picture on that of just many disks and lines and points. So these numbers can really get huge, right? If you want to. So that's what a cell decomposition should be. And the point is now, and that's the interesting part about that, while these, of course, the cell decomposition is far from being unique. You see, the numbers that you need of points and lines and disks is not unique. But there is a certain combination of these numbers that is unique. And that is if you take the alternating sum of these numbers. So if you take this minus that plus that, so 1 minus 1 plus 2, that is 2 in that case. Here, of course, it's the same number, but also here, 2 minus 4 plus 4 is also 2, and that's not a coincidence. And that's a general statement that we'll need here. So there's a lemma and definition. But again, lemma, of course, in the sense that the proof will just be a sketch proof, is the following, that, so in the above situation, so that means X is a whatever, right, 2-dimensional compact orientable manifold. So in the situation above, the number was usually denoted by the Greek letter chi, and it's sigma 0 minus sigma 1 plus sigma 2 depends only on X, only on the topological space, and i.e. not on the chosen cell decomposition. It might look a bit surprising because there's so many choices of doing, but well, in fact, that goes into the area of algebraic topology, and probably maybe in commutative algebra you had seen things before like that. You take alternating sums of things that become then well defined when you consider exact sequences. But let me just give you like a quick topological reasoning here why this is true. So the point is, it's essentially 2 observations for the proof. So the first one is that if we start from a given decomposition, there's a way to refine that in a sense, essentially in two different ways. Namely, I could add more points or add more lines. And in both cases, actually, this number chi will stay the same. So note first. Under a refinement, I don't want to again define that. I don't want to define that rigorously, but just show in a picture what I mean. And the refinement of the decomposition the number chi remains invariant. remains the same. So what do I mean by refinement? Refinement essentially means taking more points, taking more lines. And so there's two ways to refine that. First of all, let me maybe draw a local picture of what this might look like. A decomposition. So we have a certain number of points. And then you have a certain number of open disks. So that goes on somewhere. And then we have a certain number of lines and disks here. So that could be a local picture of such a thing here. And the first way what you could do is that you add another point on a line. So you couldn't add a point in the middle of the disk because the remaining thing wouldn't be a disk, right? That's not allowed. But you could add a point on a line, and then it would look like, so if I take the right line here, for example, and we had another point here, and then it looks like I'm going on somewhere here. And what that does is that it keeps the number of disks the same, obviously. So the disks haven't changed. But we have 1 point more and we have 1 line more, because like this line got separated into 2 and we have 1 more point. So that means our sigma 0 becomes sigma 0 plus 1, and sigma 1 becomes sigma 1 plus 1, and sigma 2 stays the same. So it's still sigma 2. Or we could add a line between 2 points. So for example, now if we have this, we could add a line between those 2 points. And so we could also add a line to a disk. And then it might look in the picture here as follows. Here, so we still have the other one here. And the point, here's the point, here's still the same points. And that's the same disk as before. And now here we have in the middle, we have 2 disks. So that's a similar type of operation. Now we have just, so the points are still the same, but we have an additional line. So we have 1 more line, and that also separated the disk into 2 disks. So we have 1 more disk. So an operation like this will keep sigma 0 fixed. So sigma 0 goes to sigma 0, but we get 1 more line. And we get 1 more disk. And that means if you only do operations like that, which we would call a refinement, so you take more points, more disks, then in both cases, obviously, this number remains the same. So that's the first observation. So when you make refinements of your decomposition, then the number chi remains the same. Okay, in both cases, all this number chi is constant. And in general, a refinement would be obtained by a finite sequence of steps like that. And then the observation, so that's the first part. And with this, the point is that any arbitrary 2 composition have a common refinement. And the picture for that is essentially that up there. So if you start with this one here, with those 2 refinements, which have nothing in common pretty much, then you can make this one from both of them, which is a refinement of either of them. So you can, for example, go from this one to the one there by just adding this point and then adding this line and then adding this line. So essentially, you first add all the points that you have in both of them, and you add all the lines that you have in both of them, and you get a common refinement. This now every 2 decompositions have a common refinement. And so they would have the same number chi. And that's the argument here. And so that means this number really, I mean, of course, that's the idea for an argument. And so that means the number chi depends only on x, and it's usually called the Euler characteristic of x. The number chi called Euler characteristic, or topological Euler characteristic. There's many, I mean, probably you've seen Euler characteristics before in other circumstances, but that's the topological Euler characteristic of such a space. As you might imagine, this Euler characteristic is now related to the genus. And let's just figure out how. So maybe call this an example. So how is the genus related to the Euler characteristic? Let's just draw the pictures in. So a genus G curve, or genus G surface, real surface, complex curve would look like this. So with G handles. So the G is the number of things here in the middle. And we want to draw just a cell decomposition. And we can do this in any possible way. So make your favorite decomposition. We are guaranteed to always get the same number. I guess the easiest way to see what the numbers actually are is that if you think about this maybe as a donut, is you just cut this twice by a plane. And you just cut it horizontally once, and then you cut it vertically once. What does that look like? So the points, what we get there, we first draw this. So the points that we'll get will be exactly those points here. And then if we cut horizontally, that means we will get these lines here on this. And then we also cut horizontally and get one line here and one line there. So that's the first thing here. And then we take another cut, which is, I should have drawn the picture better, I guess. Is we can now make a vertical cut like that. And so then the picture looks like, what is it here? Yeah. So that gives us essentially something like this here. And here. And on like that. So maybe if we draw it first in the better in the genus 1 picture, then what we get is just 4 points. And then we down there. There, right? So that would be the corresponding genus 1 picture. So that means we make one cut like this. There's also the horizontal one here. And one here. Just cut with tape. So imagine like taking a donut, then slicing it like this. Like you just open it as if you want to put some butter on it, and then you make one vertical cut. And then it looks. So, and then you just count, right? So what is the number sigma 0, sigma 1, sigma 2? And that is in fact here quite simple to do. The number. So sigma 0, so sigma 1, sigma 2. Then what you get is the number of points. So for each hole, you get 2 points just at the hole, and then one at the left and one at the right. I forgot that yellow one. So that means it's a 2g plus 2. And the number of lines is very similar. So at each hole, you get like the 2 lines just at the hole and then 2 lines right next to it. So that gives a 4g. Like these 4, those 4, those 4, and so on up to those 4. And then you have 2 more at the left and then the 2 big ones here. So we have a plus 4. And sigma 2 is quite simple because you just like have the upper half and the lower half, and so you cut it twice, right? You cut it here, you cut it there, you get 4 pieces. So that means you get 4 of them here. And so that means the alternating number. So chi is 2g plus 2 minus 4g plus 4 plus 4. Yes, so the 4 cancels, you get a 2, and then the 2 minus 2g. So that means chi is 2 minus 2g. And if you solve for g, then you get 1 minus chi over 2. So what this means, if we can compute the Euler characteristic, then we have computed essentially the genus, namely by taking 1 minus chi over 2. So there's probably a better picture in the notes for that, where it's easier, can be seen easier. To say solving for g means g is 1 minus. And so that means these Euler characteristic and these cell decompositions are essentially a tool to compute the genus. So that means, and that's what we will apply. We will apply this to our complex curve. So that means we have a complex curve. We'll find the cell decomposition, and then we count the number of points and lines and disks, and then compute chi and plug it into the formula and get g. Right? So that's the idea for the whole thing. Are there questions? Okay, let's see how far we can get. So let's do the actual proposition. That's usually called the degree genus formula, or let me just call it the topological one, because there will be different definitions of genus. So the topological degree genus formula. It says the following. So in the complex case, actually, like the genus in that case, in contrast to the number of loops or real curves, is actually uniquely defined. So it's not just a bound, but it says it's always the same number. Namely, every projective curve over C has topological genus. As I say, the same number pops up again, minus 1 choose 2, this time without a plus 1, where D is its degree. That's the result. So again, we get the same number, but this time the proof will not be the same. So it's like maybe examples first before we do the proof. Let's see how far we get in the proof. Maybe we continue next week then. For examples, we've seen these numbers like now twice in the propositions before. Now it's just now without the plus 1. So for d equals 1 and also d equals 2, you will get this number again, g. So we'll get g equals 0. That means we have a sphere, which at least for degree 1 is not surprising, because for degree 1 it's just a line. A line is a P1C. P1C is C union infinity. That's just a sphere. So there's no holes in that. And in fact, the degree 2 case gives the same. If we had a notion of isomorphism of curves, we would see it's an isomorphic curve. We don't have here, but So there you get the same result. And the first interesting case would be degree 3, where you get, if you plug it in, get genus 1, and that would be an actual donut, right? So a curve like this. So where the genus is 1, you just have the torus. And then in the next degree 4, you will get 3 holes in there. So not every number occurs, not every genus on those curves. But yeah. So those cubics actually, like where you get a torus, I mean, they will play an important role again later in the class. But at the moment, we're just interested here in the topology. Yeah, so that's the result. Let's just start with proof, maybe. Just 10 minutes. And so, as I said, the idea is to come up with a cell decomposition of the thing. And that we will actually get by a projection down to P1. And that looks as follows. So let's say we have such a projective complex curve. Again, of course, sketch proof because it uses all that stuff from topology. So say let F be projective curve over C. And say D, of course, is the degree. And the first thing we want to do is project it down to a P1. So that's one of the key points there, namely by a change of coordinates. So we can, first of all, change coordinates. That doesn't change the topological type or the degree. You only have a very mild condition, namely I want that this certain point 0, 1, 0 in P2 is not on F. So that's likely to be the case anyway. If not, we just make a linear change of coordinates. And we consider then the following map. Of this pi, the projection. And it starts from V of F and goes to a P1 over C. And it sends the points X, Y, Z to, I just leave out the Y. And so it just essentially goes from P2 to P1 by just leaving out one coordinate. The one point is just we have to make sure that the result is not 0, 0, because 0, 0 doesn't exist. And that's why we have to exclude that 0 something 0 that stands here. That's why we don't want the point on VFF. Right? But if that's not the case, then this is a well-defined map on VFF. And of course, in affine coordinates, I've written it down in projective coordinates, but in affine coordinates, that means where z equals to 1 and x and y are the coordinates, that would look like x, y goes to x, and that's just a projection down. Right? So it's actually a projection map. So if we draw a picture then and draw the affine case, then here this would be P1, here would be V of F, sitting somewhere here in the plane, and we just map it down with pi with an actual projection map. Right? Now, what does that V of F look like? Now, for a given point in P1, so if I have any point in P1, what is the inverse image here? I mean, how many points do we have lying over that? So that just means that we plug in certain values for x and z and see how many y's we have that satisfy the equation f of x, y, z is 0. Now, f is an equation is a polynomial of degree d. That means in general we will have d answers, right? D solutions. As the degree of f is d, so a general point, say x, z in P1, will have d inverse image points. Under pi. Right? So that means if we have a point here, then we have a certain number of points up here, and that's just d points. In most cases. Of course, it's always d counted with multiplicity. And if we move the points here around, it might be that at some places we just don't see D distinct points, but maybe we just see D minus 1 point, and one comes with a multiplicity of 2. Or even higher multiplicity. And that will in fact happen. So we cannot avoid this. So let's have a look at what happens then. So let's note at some points in P1, so it means at some points xz in P1, 2 or maybe or more of the inverse image points may come together. They coincide. And this will happen in general, but again by a suitably general choice of coordinates before we can make it. So this will only happen with 2 points coming together and not more than 2. So again, that's something that would have to be done in more detail, but we're doing a sketch proof here anyway. So say by using or by applying suitably general coordinate transformation, we can assume that that at some points in Z we have exactly D minus 1 inverse image points. That means exactly 2 coming together. i.e. exactly 2 zeros coming together of the corresponding polynomial, so x dot z, so where we have a fixed xz and see whatever the values of y, so exactly 2 of the zeros of that come together. That means there will be a couple of points here where we only have D minus 1 inverse image points. That means where 2 of them here come together. So if we draw a picture of that, that would sort of look like this, which is a misleading picture again, because that sort of looks like a singular point, but it's not. It's just like locally, it's a map like a complex number goes to a complex number squared. So same with like square root function over the complex numbers, right? So over 0, there's only 1 complex root. Over all other points, there's 2 complex roots. And neither the complex plane upstairs nor downstairs is singular. It's just that we're drawing a real picture, which is sort of wrong, and that's why it looks singular, but it actually isn't. So we have a certain number of points here where there's only D minus 1 inverse image points. 2 of them come together, and the other stay the same. So these points here where this happens, I mean, they are usually, just give them names, they are usually called ramification points. And that's what the general map will look like. So that means we do have a projection over an arbitrary point. We'll have the inverse images, but there's a couple of ramification points around somewhere. And there will be more of them then, of course, right? So like, again, with the same note as before, that's a real picture, which is sort of wrong. So these points are ramification points. And what we want to do now, but probably not today, is we then take off the P1 downstairs. Let me just say stop there, continue next time. For the P1 downstairs, we pick a cell decomposition. And we do that in such a way that all those images of the ramification points are part of the cell decomposition. Right? And the rest will just be lines and planes and disks. Right? So now it's the real picture. You don't really see the disks, but they're somehow there because actually it's a P1 over C. And take the inverse image of all these things. Right? And as away from these points, nothing happens. It's just like a D-sheeted cover. So you just see D copies of that thing. That means like the inverse image of every line will just be D lines. The inverse image of every disk will just be D disks. But the points here that you have, they will not have D inverse images, but just D minus one of them. And that means we start now then with a cell decomposition down there. We know how many cells we have. We just start with some. And then count essentially the cells up there and just do the math and see what the result is. Right? For that, we would have to know how many ramification points we have, because that's just the number. I mean, for each ramification point, we have one inverse image point less. But the number of ramification points can actually be computed by Bézout, because how is that? But as I say, I do this in more detail next time. That's just because, when two of the zeros come together, that's when this polynomial has a double zero. So that means when the partial derivative with respect to y is zero as well. That means the equation for the ramification points is that f is zero and df by dy is zero. So that's two curves. And as df by dy has degree d minus 1, they will intersect in d times d minus 1 points. That means we will get exactly d times d minus 1 ramification points, and the rest is just then doing the math, essentially computing that. But again, as I said, I do it in the next time in more detail. And then we are sort of done with the applications of Bézout and can move on to some other things. All right, so if there's no more questions, then or are there any more questions? Otherwise, I'll just stop for today.